This is the second part of the amine chapter. And we're going to talk about alkylating the nitrogen. All right, when you alkylate a nitrogen, you're basically adding a carbon to it. And we're going to do the alkylation with ammonia first. So we are going to take ammonia. We're going to add, let's add methyl bromide. This is going to be an SN2 reaction. The nitrogen is going to attack the carbon and displace the halide. So we're going to end up with a methyl. And for a little while, of course, the nitrogen is going to have 4 bonds, so it's going to have a counterion associated with it. But assuming that you put enough ammonia in there, the ammonia that you have in excess can come and, I'm going to put 2 hydrogens here at the bottom and 1 showing there. So the excess of ammonia can help deprotonate your nitrogen. So that's how you get the free base, methylamine. And you're also going to get, of course, an ammonium bromide molecule. But of course you're going to need an excess ammonia to do this, and you can alkylate the nitrogen this way. Unfortunately, something is happening here because the ammonia had 3 hydrogens attached to it, to the nitrogen, and the hydrogens cannot donate to the nitrogen. But when you put a methyl on the nitrogen, now that methyl can donate a little bit of electron density to the nitrogen. So this nitrogen is slightly more nucleophilic than the ammonia. So what's going to happen is that you're going to alkylate a second time. There's nothing you can do. You can measure as much as you want, and this nitrogen, the methylamine, is still going to be more nucleophilic. So now you're going to have 2 methyls on your nitrogen. I'm going to go ahead and deprotonate right there, because now this one has 2 methyls, so it has 2 groups donating to the nitrogen, so that the dimethylamine is more nucleophilic than the methylamine. So we're going to add a 3rd carbon, a 3rd methyl group onto it. And you can imagine what's going to happen, because now I have a tertiary amine, and the tertiary amine, we have 3, and that should be just 1. That's just 1. I'm sorry, I apologize for that mistake. And the tertiary amine, again, is more nucleophilic, so it picks up a 4th methyl. So this is the problem with the alkylation of amines. It doesn't matter how carefully you do the reaction. You're going to end up with multiple alkylations. So we try not to actually do direct alkylation of the nitrogen. This is going to give you a horrible mess of primary, secondary, tertiary, and the ammonium salt. So we don't try to alkylate amines directly. We do it indirectly. But before we get there, let's study that nucleophilicity that we were talking about. So I have ammonia right here, and I have the methylamine. And again, the methylamine acts, the methyl can donate electron density to the nitrogen. It's donating through that single bond, so it's an inductive effect. And that makes this nitrogen more electron rich than the original nitrogen of the ammonia. And of course, if it's more electron rich, it's going to deprotonate, be basic or be nucleophilic. Much better than the ammonia. Now there's one exception to that, and if you happen to have aniline or any aniline derivative. So I have aniline right there, And what's happening in aniline, and I promise you this in color would be beautiful, but I don't have it, is that you have the delocalization of the aromatic electrons in there, the 6 pi electrons of the ring, but you also have a lone pair right here, and that lone pair can be delocalized in the ring. And this is what it's showing right here, a much bigger area of delocalization that includes the lone pair on the nitrogen. If we use that lone pair to pick up a proton, then we're reducing the delocalization of electrons. So basically the aniline with the lone pair, the nitrogen with the lone pair, it's more stable, and that's why when you have aromatic amines, they don't seem to be as basic as any open chain amine or any other alkylamine. So this is what we do. We try to use other groups aside from just the alkylation, the direct alkylation of the nitrogen. So cyanide or nitrile, it's easily converted into a primary amine with reducing agents like lithium aluminum hydride. Or if you want to do a hydrogenation reaction, because remember there's a triple bond between the carbon and the nitrogen. So I can hydrogenate the triple bond, and I am going to end up with a primary amine. So this is a nice and easy reaction. We put the cyanide wherever we need it through an SN2 reaction, and then we just reduce it. The next one is the azide displacement. And the azide is an N3 minus, and this is the Lewis structure of it. Notice the nitrogens on the outside are negatively charged, both of them, so they have 2 lone pairs each. The nitrogen in the middle has 4 bonds, so it's positive. So either of the outside nitrogens can be nucleophilic, so they can do a nice SN2 reaction. Again, make sure that if you're doing an SN2 reaction, you're following all the rules for SN2. So you replace the bromide, you substitute the bromide for the azide, and then we're going to reduce the azide using lithium aluminum hydride again, and you are going to get the primary amine. The difference between this synthesis right here and the previous one, the cyanide group, is that this synthesis will not add carbons to the ring. When you add the cyanide to the alkyl halide, you're increasing the number of carbons by 1. But this one doesn't do that. If we're talking about aromatic amines, then the easiest way is to put a nitro group on the benzene ring with nitric acid and sulfuric acid. And then you can reduce the nitro group doing a hydrogenation reaction with hydrogen and nickel. There are other ways to do this exact same reaction, like for example, you can use a transition metal with HCl. Of course, you're going to need to neutralize your HCl at the end, but you reduce the NO2 to the amine. Needless to say, this will only work for aromatic amines. Now the Gabriel synthesis, it's a little longer, but it's quite effective. So this is phthalimide right here, and phthalimide has a hydrogen that's basic, or acidic I should say, sorry. With potassium carbonate, I can deprotonate the nitrogen, making it negative, a good nucleophilic carbon, and I can alkylate it with whatever I want. Let's say I want something small like ethyl bromide. So I add ethyl bromide, the nitrogen is going to do an SN2 reaction, it's going to attack my carbon and displace the halide. And as long as you follow your SN2 reactions, your rules, this is going to be a good alkylation. So we just attached an ethyl group to our nitrogen. I'm missing a ring right there. So this right here, this is the amine that we want. This is just an anchoring group, if you want to call it that. So it's anchoring the nitrogen. It only allows for the alkylation of the nitrogen once, and you're done. Now we need to get rid of the anchor. So what do we do to get rid of the anchor? there's two possible ways. Let me just go ahead and redraw in here. The anchor, what I have right here is an amide, and I can hydrolyze it. So if you wanted to add sulfuric acid, water and sulfuric acid, and then just heat it up, reflux it for a couple of hours, then you can do that. You will get CH2, CH3. As long as you keep acidic conditions, you're going to get a salt, your ammonium salt. But if you neutralize it, then you get your free amine, your free base if you want to call it that. So a little bit of sodium hydroxide will neutralize it and you get your free amine. The most common way of doing this, it's adding hydrazine. We have used hydrazine before in the Wolff-Kishner reaction, but what we're doing with the hydrazine is that we're going to basically substitute this nitrogen for the hydrazine right here. So the hydrazine is going to take the place of the amine that we need. Hydrazine, the two nitrogens are connected to each other, and each has a hydrogen to it. That's not the amine I want. The amine I want is the ethylamine. So the Gabriel synthesis is a good alkylation. It can only alkylate the nitrogen once, and it also produces a primary amine. Unfortunately, we already have several ways of making primary amines. So in part number 3, we will talk about other ways of making secondary and maybe tertiary amines. So go to the third part.